Hello and welcome back to another session here on LRVS 2021. And um, so slightly bittersweet in that this presentation was supposed to be presented by Cristian Soto, for our team members at Fluitec. Sadly, he had to do some emergency surgery. We think he's okay, but we wish him the best and a speedy recovery. But I'm also happy to present my other good friend, Greg Livingstone, who's going to do this for Cristian. This presentation, Exploration of Varnish Compound Solubility in Working Systems. And just before we get into that, I want to remind everybody, this is the code. This is the play to win code. So please mark this down, put it in the play to win section of the app. And then with that, without further ado, Mr. Greg Livingstone.
All right. Thank you, Josh. Pleasure to see you all. And I am not Dr. Soto. My apologies for having a less educated, not as good looking version of Cristian, but hopefully we will have him back here with us shortly. I will be talking about the exploration of varnish compound solubility in working systems. You'll get an idea what that means here shortly. But what I'm going to talk about today, number one, I'm going to talk about a quick overview of oxidation and also solubility. Number two, I'll introduce this concept of a solubility enhancer, some of the initial long-term field performance observations that we had, our efforts to develop a long-term performance solubility enhancer, and share some field results from that. So to start off, let's talk about oxidation and solubility. And in the world of oxidation, this is a really important process that really happens virtually to everything and everybody. And oil is no different. And it all starts with the removal of an electron. We used to think that oxidation was really based on the presence of oxygen, but actually now we've kind of refined the definition. If you remove an electron, it essentially will create a free radical, and that can in fact happen in the absence of oxygen. But this reaction, these free radicals will continue to react in an autocatalytic way until something stops it and terminates this reaction. This rate of reaction is also sped up by various different catalysts, such as wear metals, especially copper and iron. Heat will really speed up the rate of reaction, oxygen or air that's getting in the system, and water as well. So we have our little free radical, and this is what we would term as the initiation part of the process. The next part of the process we would refer to as propagation. And the propagation phase is when we have these free radicals that are now undergoing changes. So the free radicals may in fact react with, hopefully, will react with primary antioxidants such as amines or phenols, hopefully, and will kind of neutralize or stop that reaction. They can also continue to degrade, turn into hydroperoxides, which in some formulations could be reacted with secondary antioxidants. Zinc dialkyl-dithialphosphate, or ZDDP, is a common secondary antioxidant that many people are familiar with. So that will react with the hydroperoxides. All of these reactionary products will turn into higher molecular weight oxygenated byproducts that eventually in this termination phase, these molecules are somewhat polar in this non-polar environment. So they have a tendency to agglomerate and polymerize together. Why do we care about this, and why is this so important? Well, actually, this will have a pretty big impact on the lubricant. So the lubricant, we're looking at physical changes to the lubricant, such as sludge formation, varnish formation. In some cases also we see viscosity increases, as well as chemical changes. So we'll actually see the acidic constituents in the oil grow, and then you'll see an acid number increase as well. So all of that leads to some of the problems that we want to try to address now. So some of the results of oxidation, all sorts of gooey, sludgy materials that, as you can imagine, are not so good for the reliability of equipment. So I think one of the questions that we've pondered and spent some time working on is, what can we do to impact this part right here, the physical changes? Is there anything that we can do to influence how and where and when these degradation products come out of solution and cause some of these problems? But actually, before we get to that, we actually need to understand a little bit about solubility. The basic principles of solubility is like dissolves like. So if you have two materials that are somewhat similar together, they will dissolve. So there's several. How do you know if materials are similar? There's several different ways of looking at this. So one is polarity, what we have up on the screen. Another is the energy of vaporization. How much energy is required to convert that substance into a vapor? And it just so happens that hydrocarbons that have similar energy of vaporization rates actually are more soluble together. And so one of the ways that we like to look at solubility is a matrix that was developed in the in the water world. It's also used for helping understand what solvents can dissolve paint, so in the painting industry, but they're referred to as Hansen solubility parameters. And in this, we are not just looking at polarity, we're also looking at hydrogen bonding, and actually we're looking at dispersive forces. And with this, we can build a 3D model. And if we understand the composition, chemistry, and some of these properties of the varnish, we can then create a solubility enhancer that will encompass that. And based on this Hansen solubility parameter, this is a good tool to predict what will be solubilized in the oil and what will not. It also helps us understand when varnish will come out of solution and what its solubility is in oil as well. So that's a little bit about solubility, and our efforts have been to develop a solubility enhancer. And so can we actually put something in the oil that will completely encompass the characteristics of the varnish, dissolve it, so we don't actually end up with some of this image that we see here on the right with extremely degraded, sludged up lube oil systems. So the solubility enhancer is actually a really effective way of decontaminating a lube oil system in between oil changes. It works by increasing the solubility of the in-surface oil. And when you increase the solubility, you now allow the oil to actually dissolve some of these organic soluble degradation products that have settled out and formed. And one of the benefits of this over, say, using a surface active agent like a dispersant or detergent technology is that the varnish is essentially dissolved one layer at a time. So you don't have a big sudden dump of contaminants. And also, once it's dissolved, it's held in the oil. This is not like, say, an additive that is sacrificial, that will deplete over time, that you'll have to replenish over time. And so it actually works out to be a very effective way at decontaminating and desludging lube oil systems. So we also would refer to a solubility enhanced flush as well as maybe an alternative method to decontaminating lube oil systems instead of introducing chemicals, some of which are sometimes incompatible with the lube oil system and can also impact the long-term performance of the new charge of oil. So a solubility enhanced flush, essentially you are dissolving kind of one layer at a time the sludge and varnish in the system and leaving everything, all the oil wetted surfaces nice and clean and ready for your new charge of oil. So this is good. We have a solubility enhancer that works on the short term. Is it possible to develop a solubility enhancer that can work long term? That maybe can be a long term deposit control technology in a varnish susceptible lubricant. So we spent some time looking at this and looking at some chemistries of solubility enhancers that have been used in the field. And so this was a observation of one such solubility enhancer. Very high MPC. They introduced a solubility enhancer. That MPC dropped down, and actually over the first 6 months, everything looked good. Then the MPC started climbing up, and then the servo valve started sticking, and then they actually ended up with actually much higher MPC values than they originally started with. So a year after introducing a solubility enhancer, it actually created more deposits than before. So so not all solubility enhancers are created equal, and so we wanted to see if we could develop something that not only works short term to decontaminate lube oil systems, but can also provide some long-term results. So if you saw my earlier presentation, we talked a little bit about this accelerated oxidation test that we have that we refer to as the turbine oil performance prediction test, or the top test. This is a fantastic tool for helping us benchmark different formulations of turbine oils and understanding what oils will function well under extreme accelerated oxidation stress. However, it also has been a really invaluable tool for us to understand what solubility enhancers can work. And if we put a solubility enhancer into a formulation and then really accelerate its oxidation, what will happen? So the principles of the test, basically we are putting several 350 mil test cells into a heated bath that we heat to 120 degrees with catalysts and air bubbling through it, basically to try to kill the sample. And then we'll take each tube out at a designated period of time. In some cases, maybe once a week, or in other cases, once every 3 weeks, and see what kind of chemical and physical changes happen in the fluid. And so doing this with solubility enhancing technologies, we saw actually a pretty big difference in performance. So here we have a baseline with in-service oil with a fully formulated oil. And what we're looking at here are the MPC results and actually the weight of that MPC patch after 6 weeks in this accelerated oxidation test. So here we have an in-service oil ended with an MPC of about, a fully formulated oil ended with an MPC of about 60, and the weight of the patch is actually on the right-hand y-axis here, so approaching 600 milligrams per liter of weight on this patch. We put a solubility enhancer in it, and in some cases, in this case, the results, we actually saw a higher MPC, but actually a lower amount of weight on the patch. Let me just preface the weight on the patch. The MPC, I have a fair degree of comfort with the reproducibility, repeatability of this test. The weight of the patch, there are methods of making this actually more precise, but just weighing the MPC patch, I would say there's a fairly large margin of error. So at least plus or minus, say, 100 milligrams of sludge. So, but there is certainly a difference here between the baseline and solubility, baseline with the solubility enhancer 1. Then solubility enhancer 2, we ended up both with a lower MPC and a lower amount of weight on the patch. The chemistry we actually saw in the field, that we observed that in the course of a year, the MPC started skyrocketing, is this solubility enhancer number 3 right here. And in fact, what we saw is the MPC in this test went up as well. And it may have had a little bit of an impact on the weight, but I would say, again, these are probably within the same margin of error. The MPC skyrocketed, and also on the glass coil, the catalytic, or the glass tube and the catalytic coil, lots and lots of deposits here over an extended period of time with this solubility enhancer. And then finally, with number 4, we saw very, very low MPC values, no stain in the glassware whatsoever. It appeared like out of, at least with these 4 different solubility enhancing technologies, that this product appeared to perform pretty well in this accelerated aging test. So Accelerated aging tests, I think, are a fantastic tool to simulate what may in fact happen in the field, but it's not the same as actually a real life field experience. So we sometimes compare this to, say, an egg. If you have an egg and you incubate it and wait for some time, it will turn into a chicken. But if you heat that up a little bit, you're not going to have a chicken. You may have a hard-boiled egg. So there's not always a direct comparison between accelerated oxidation tests and actually the end result, what you see in the field. But at least this is a good estimation and gives us a little more confidence of introducing this in the field. So this is an example of a 2-year case study with, in this particular case, in this compressor train, there was extremely high bearing excursion temperatures that was caused by basically this varnish creating an insulating layer on the bearing, causing the temperature to spike up. Then that bearing would eventually, that layer of varnish would get so big that the bearing would then just wipe that layer of varnish free, allowing the oil to do its job of insulating that bearing. You see that big drop in temperature, but over time, it's common to see with this sawtooth type signature, you'll see the bearing temperature increase here over time as well. But these bearing excursions are certainly very concerning for an operating system. And you can see the results here, both in Fahrenheit on the left side and the temperature of the system, or the bearings in Celsius on the right side. We added solubility enhancer to the product, immediately saw a temperature drop, and actually over the last 18 months have seen this basically flat line. So we were able to verify that what we observed in the field in this accelerated oxidation test actually also performed well in field application as well. So this is just a little bit of our journey that we have that we've gone through over the last several years of seeing if there is a way of trying to come up with a technology that can be added to in-service oils that can not only help short term to decontaminate lube oil systems and assist in many cases replacing chemical flushing and allowing you to maybe a simpler way of allowing you to decontaminate the lube oil system in between oil changes, and how our journey has evolved into trying to develop a technology that can work long term as well. So to summarize, understanding solubility is really a key to addressing lube oil varnish, which in most cases is a symptom of oxidation. And so there are different ways of understanding solubility. The basic principles of like dissolves like is something that I think we all can relate to, where we all are, we know that oil and water don't mix because they're not similar. The composition of oil and water are not so similar. We have found it very helpful to use the Hansen solubility parameters to really predict what solubility enhancing technology could be most effective at dissolving varnish. And we've been able to demonstrate and compare different technologies in accelerated aging tests in the lab. And finally, we have found a solubility enhancer that not only worked well short-term to dissolve varnish, but also provides long-term deposit control performance as well. So thank you so much, and I appreciate you paying attention and joining another session here at LRVS 2021.
Hey, Greg, thanks so much for stepping in for Cristian. And it looks like we have a number of questions that we could run through. And well, first of all, thank you those for the well wishes to Cristian, and we'll pass them on. But Chris is asking here, is acidity increases trigger any concerns with varnish?
So it's high acid number within the oil trigger a concern for varnish mitigation. So I think there's a couple different ways that you can look at this. Certainly, high acid number you should definitely pay attention to. So if you have an elevated acid number, that is suggesting a lot of oxidation has taken place. In some chemistries, there are some acidic additive components that are used, and in those cases you may actually see the acid number come down before you see it go up again due to oxidation. But yes, you should definitely have concern if there is an elevated acid number, and I would say there's not a direct correlation to varnish, but there is an indirect correlation or an indirect relationship between the two. The other way of looking at this is if your varnish mitigation technology is working or not based on acid number, but I'm not sure if that's what you were referring to.
Thanks for that, Greg. And another question from Luder Quick. I don't. If it's up there, there we go. So, is it known in what way the solubility enhancer oxidizes?
So that's a very important question because these, as we just saw with the accelerated aging tests, different solubility enhancers, they may work short term, but then they could actually go on and oxidize and produce a whole range of other chemistries. There's one in particular that will create varnish that is in fact very different than varnish that mineral oils create, and normal varnish mitigation technologies are actually ineffective at trying to remove these things. So understanding the oxidative stability and what happens actually to the solubility enhancer is really critical. And so what we have also done is taken just a neat solubility enhancer, oxidized it to the under extreme conditions to see what happens. And in some chemistries, you see all sorts of deposits form. In other chemistries, and the chemistry that we've selected, actually there's no deposits. And so that is a really, really good question because yes, the degradation products of solubility enhancers can in fact go on and cause other problems if you're not using the right technology.
And that sort of leads into another question here, Greg, of like essentially how long can you leave the solubility enhancer in the oil?
That's a great question. So a solubility enhancer is unlike additives that may be sacrificial in nature. You are permanently changing the solubility characteristics of the oil. So in fact, it is as long as you're not selecting a technology that will oxidize and create problems at some point in the future, which some technologies can. The limit or the life of the solubility enhancer is really when the oil still can become saturated. This is not like it's not a technology that will forever solve any varnish problems. You can add this into this in-service oil. However, at some point, you're increasing the solubility. At some point, the oil still may reach saturation and varnish can come out. So when you use a solubility enhancer long-term, it's really important to continue to run the MPC test. And that's an effective tool to helping measure basically kind of how full the bucket is, how full the oil, how much contaminants it can still hold. And at some point, it may be possible to add more solubility enhancer to the oil to extend the life, especially if the antioxidants are healthy and the oil suddenly has gotten the solubility enhancers done everything it can do to keep things in solution. In some cases, it's possible to add more as well. And then also the second part of this question, does the solubility enhancer remove varnish from the piping internals of the system or just from the oil itself? And the answer is yes, both. So it is very effective at removing degradation products actually in the oil. In many cases, I think some of us in the oil industry really get excited when we see big drops in MPC values, but often in the field, customers are less concerned about this. They're like, is my system clean? And so that's really the measurement. Thank you.
So that's interesting. That the first part of that comment from Chris, Henry's essentially on top of that. So you put it in, right? And so where does it go, right? Does it continue to stay in there? Is it technically still in the oil, but no longer to plate out?
Great question. Yeah, and I would say this is a very common question. Did you just mask my varnish? It's still in the oil. Can it still cause problems down the road? So I think that's a really, really good question. Basically, these oil degradation products are somewhat inert. They've already reacted. That the oxidative process has terminated. So there are these somewhat inert substances that really only start to cause problems when they come out of solution. When they come out of solution, they find other particles that they're similar to, agglomerate, polymerize, settle out, form varnish, cause all sorts of concerns. But having these somewhat inert substances hanging out in the oil, that can actually, they can stay in the oil long term without having any adverse effects. So, so that's a really, that's a very important question.
So I guess that answers Anshuman's next question of what happens to the physical properties of the oil, right, due to varnish.
Yes, so great question. One really important point that I think I neglected to make is that you cannot really put a solubility enhancer into the oil if there are any adverse effects to the physical or chemical properties of the fluid. So if we're adding a solubility enhancer to the oil and suddenly the demulsibility is no longer stable, that's not going to work. If there's suddenly a steam leak in a large turbine, you're going to potentially wipe a bearing. So the number one first rule is if you're adding anything to the in-service oil, there can't be any adverse effects. But getting to Anshuman's question on if you have this dissolved varnish in the oil, how is that impacting the physical properties? So that's a really good question. Long term, we would hypothesize that the acidic constituents in the oil would rise. But it's really interesting with the solubility enhancing technology that we use. We've used this long term in the field, and in a very, very long term tests in accelerated aging tests. And actually, we don't see an increase in acid number, even though we would guess that we probably would. So I think there's some kind of there's a reaction going on that's at least neutralizing those acids. So I think the most important thing, if you're using a solubility enhancer, you don't just it's not like a plug and play, leave it and forget it. You really still need to continue monitoring all of the other parameters of the fluid in your long-term condition monitoring program. Great question.
And another one from Anshuman is about the compatibility of the solubility enhancement studies for the entire spectrum of the lubes, for gas turbines, compressors, PAGs, POs. So where can we use these or not?
Great question. So yeah, this is not widely compatible for all fluids that are used in the lubricant space. Really, the solubility enhancers are ideal for Group 1, Group 2, Group 3, Group 4 oils, so mineral oils and PAO-based fluids. I think in the majority of studies that we have done, they don't have an impact on AW or in anywhere additives or on extreme pressure additives, but we've not done a lot of testing on highly detergent or dispersant type formulations. So say, for example, in natural gas engine oils or in diesel engine oils or gas engine oils, we don't have a lot of experience yet putting this technology into that. So we would probably advise against using this technology in a dispersant technology. And once you get into the world of Group 5s, there are so many different synthetic chemistries out there. PAGs, for example, are pretty highly incompatible with mineral oils. We would not recommend the use of this in PAGs either. Great question.
All right, so there's a few follow-ups from Henry that are pretty interesting. So essentially, if we're saying that the varnish material is still in the oil, how come it doesn't show up on the MPC?
So the MPC is not measuring oil degradation, all of the oil degradation that the oil has ever seen. What the MPC is measuring is what contaminants in the oil come out of solution after that oil has been mixed with solvent, sat and incubated for 72 hours, and then filtered through a 0.45 micron membrane. And then we're measuring the color. And essentially, all of these degradation products are in the oil. It's not coming out in the MPC test because they're no longer coming out of solution. Even at room temperature, you incubate it for an extended period of time, 0.45 micron membrane has no impact at filtering out these contaminants that used to be coming out of solution but are now totally solubilized in the oil.
We're going to do one more, Greg, okay, because we have a little bit of time. So how do we ensure that the solubility enhancers in the long term don't affect the additive package or cause other problems?
Great question, Saeed. Thank you so much. Yeah, so the best way of doing this, there's all sorts of compatibility tests that you can do. ASTM D7155 is a great compatibility test that can make sure that we are compatible with when we first introduce this into an in-service oil. So that's the first thing. We want to make sure there's no reactions whatsoever when you add this into an in-service oil. However, long-term, that's really where you come into performance, tribology tests, and accelerated aging tests. And it's really important that we are looking at a full spectrum of long-term tests as well.
Excellent. So many awesome questions here, Greg. I recommend everybody connect with Greg in the platform. And maybe Greg will do a pop in the Fluitec video room. You can go in there and ask all these awesome questions. The code is here for the play to win. Please write that down. We've got to go. We've got other sessions going on. Greg, thank you so much. Thank you, everybody, for attending.
Thank you,
we'll see you next session. Bye now.
All right.